Golden Iris Productions presents Time Dilation by Mark F. Dennis. Time Dilation. This presentation explores time dilation, how the passage of time depends on gravity, acceleration, and motion. We will see why time behaves differently in gravitational fields and how this differs from time changes caused by motion alone. Core idea. The core idea is simple. A clock deep in a gravitational field runs slower. If 1 second passes on a local clock near a massive object, a distant observer measures more than 1 second. Gravity stretches time outward by placing clocks deeper in gravitational potential.
Definitions. Here are the definitions used throughout the presentation. T is the proper time measured locally near the mass. T prime is time measured far away, effectively at infinity. C is the speed of light. We consider a large mass at a fixed radius to make the effect clear and measurable. Equation 1. Schwarzschild form. This equation comes directly from the Schwarzschild solution of general relativity. It shows how 1 local second corresponds to a longer duration far away, depending on mass and radius. This equation applies to a static spherical mass. Equation 2. Escape velocity form. The same time dilation can be written in terms of escape velocity. Here, time dilation depends on the energy required to escape the gravitational field. Although this resembles a velocity effect, the velocity here represents gravitational potential, not motion.
Equation 3. Acceleration radius form. Using the relation between gravity, mass, and radius, the equation can also be written using acceleration. Solving for time shows the same result. 1 local second corresponds to a longer interval far away. Acceleration appears here because it encodes gravitational potential. Why these equations are equivalent? All 3 equations are mathematically equivalent. They rely on the same identity. Mass, escape velocity, and acceleration times radius all represent gravitational potential energy per unit mass. Time dilation depends on potential, not on force alone. A strong gravity example. Now consider a strong gravitational field where the dimensionless potential is 0.8. This represents intense gravity, but still lies outside the event horizon.
Solve for time dilation. Substituting this value into any of the equations, we find that 1 local second corresponds to 2.24 seconds far away. Time near the mass is compressed relative to infinity. Physical interpretation. A local observer measures 1 second normally. A far-away observer measures 2.24 seconds over the same interval. The deeper the clock is in gravitational potential, the slower it runs relative to distant space. Approaching the horizon. As the radius decreases towards the Schwarzschild radius, the time dilation factor approaches 0. To a distant observer, time appears to freeze at the event horizon.
Conceptual summary. Time dilation depends on gravitational potential. Acceleration alone is insufficient. Acceleration times distance matters. Large mass combined with small radius produces strong time dilation. Time far away runs faster than time deep in gravity. Velocity time dilation. Velocity time dilation arises solely from relative motion. It is symmetric between inertial observers. No absolute difference in elapsed time occurs. Gravity and acceleration. In gravity or sustained acceleration, time depends on position or motion history. Symmetry is broken. Real differences in elapsed time occur. Final takeaway. Velocity without acceleration only changes how time is perceived. Gravity and sustained acceleration change how time passes.
1 sentence takeaway.
By the equivalence principle, gravity and sustained acceleration are equivalent. Both slow yokel time by placing clocks deeper in space-time structure. Velocity versus Doppler. Relative motion changes observation, not the local process.
Velocity alters observed time, just as Doppler motion alters observed frequency. Velocity-time dilation. Velocity changes measurement, not clock behavior. Final conclusion. Velocity changes how time is observed. Gravity and acceleration change how time passes.